before we dive into details, here's a quick overview of the entire process, and there are 4 main stages. First, we mix the high purity steam and methane in a steam methane reforming reactor. The output is then passed to a WGS reactor to convert harmful byproduct. The gas mixture is then sent to a purification unit using PSA. Finally, the purification material is cleaned by regeneration and ready for the next cycle. So for this presentation, we'll be focusing on 2 major engineering courses, which are Reaction Engineering 1 and Separation Process 2. So for reaction engineering, we cover the design and the sizing of the steam methane reforming reactor. This is where the main chemical conversion occurs. And for separation process, it covers the design of PSA unit and the regeneration cycle, which ensure we achieve our final high purity hydrogen product. So as you can see here, there's the 2 type of reaction, which is the SMR reaction and the water gas shift, and those are the equations involved. But for this assignment, we will be only focusing on the SMR reaction. So the SMR reaction is highly endothermic, meaning it takes up a huge amount of heat and needs that heat constantly to work. To handle this, our physical equipment is a packed bed reactor, which uses tubes packed with solid catalyst. We design and calculate its performance using the plug flow reactor model. As shown in the table, the PFR flow pattern is the optimal choice compared to the CSTR model. It offers minimal back mixing and a concentration gradient, which is essential to achieve the highest possible conversion in the smallest volume for the specific catalytic reaction. This PFR configuration is also essential because the SMR reaction is highly endothermic, requiring excellent temperature control to prevent undesirable side reactions such as choking. For the catalyst, we have selected nickel supported alumina as the primary reforming catalyst. This is an optimal choice because it provides the best balance of performance and cost effectiveness. Nickel is highly effective for the methane reforming reaction, and crucially, it remains thermally stable under our high operating temperature. The alumina support plays a critical role. It provides the necessary large surface area for efficient gas-catalyst interaction, alongside strong mechanical stability for the catalyst bed inside the PFR tubes. Using this, nickel-based catalyst ensures high methane conversion while keeping the overall system design durable and economical viable.
First, I will explain the strategies to maximize hydrogen selectivity, which means minimizing the formation of side products like carbon and carbon monoxide. The main approach is to use high stable and active catalysts, such as modified nickel and even precious metal like rhodium. These catalysts help to suppress carbon formation and prevent cooking inside the reactor. Next, we maintain the high steam to carbon ratio, which prevent the methane cracking and reduce carbon deposition. It is also important to keep a stable temperature profile in the reactor to avoid hotspot, because hotspot promote coke formation. Finally, any remaining carbon monoxide in the product gas can be converted in a water gift reactor, which increase the hydrogen purity and reduce unweighted carbon monoxide in the final output. Next, I will explain how to maximize yield of hydrogen. Next, we focus on shifting the equilibrium of the steam methane reforming toward the more hydrogen. This reaction is endothermic, so operating at high temperature increase the methane conversion. At the same time, low pressure is preferred because the reaction produce more moles of gas, so low pressure naturally favors hydrogen formation. A high steam to carbon ratio is also essential because it drives the equilibrium forward and increase the formation of hydrogen produced. Lastly, we use the water gas shift reactor to greatly boost overall hydrogen yield because it can convert any remaining carbon monoxide into additional hydrogen and carbon dioxide.
Here is the simple flow of our simulation. First, we mix methane and steam, then preheat them to high temperatures. Next, this mixture flow into our PFR or plug flow reactor, where it heats the nickel catalyst and convert it into hydrogen and carbon monoxide. Then we cool the gas down and pressurize it to get it ready for separation. And finally, it goes through the pressure swing absorption unit where zeolite 1 react traps the impurities, giving us our final 99.9% pure hydrogen product.
So for this part, I will explain the operating condition that we use for our steam methane reforming, or we call as SMR. So the temperature we set is 910.1 Celsius. The pressure we use is 180 m. The catalyst we use is nickel on alumina. The type of reactor that we use is plug flow reactor, and the conversion we use is 0.90, and the assumption that we use is this steam methane reforming under steady state and gas phase condition. From this information that we got from the symmetry, we can calculate the initial methane concentration. The initial methane concentration can be calculated by dividing the initial flow rate divided by the volumetric flow rate. So we got that the value for initial methane concentration is 0.0024999 kmol per meter cube. So here's our stoichiometry table. For this SMR, we have two main reaction. The first one is the methane react with water. We have carbon monoxide and 3 mole of hydrogen. The second one is the carbon monoxide react with water. We got 1 mole of carbon dioxide and 1 mole of hydrogen. So we calculated all the species concentration by using information that we got from the symmetry, and we have set the conversion for 0.90. Now, I will explain how we size the plug flow reactor using the Levin spill method. For this, we calculated the reactor volume. We start with the integral. The integral represents the area under the Levin spill curve. Because we cannot integrate directly, we use the Simpson rule formula, which is shown in the slide. Before we computing the area, we first need to find the reaction rate constant, which is K. We use the Arrhenius equation to find the value of K. Next, using this value K, we calculated for several conversion points and plotted them into the Levin-Spill graph. As we can see, the curve rises sharply near high conversion, which is typically for endothermic gas phase reaction. Using the 5 data point, we applied Simpson's rule. After substituting all the value, we get the volume of PFR is 1.392 meter cube. To achieve 90% conversion, our reactor required a volume of approximately 1.4 meter cube. This confirms that the operating conditions we selected are effective, giving us high hydrogen yield while keeping the reactor size relatively small and practical for industrial application.
So once the required PFR volume of 1.392 meter cube was determined from the kinetic calculation, the final step is to quantify the catalyst mass. The bulk density of the packed nickel alumina catalyst is assumed to be 900 kg per meter cube. Then mass is calculated by multiplying volume and density, and the calculation yields a required catalyst of 1252.8 kg. This is the mass of catalyst needed to fill the reactor and maintain the targeted 90% conversion. We also estimate a necessary operational lifespan of 3 years for this catalyst charge based on typical deactivation rates due to thermal sintering and carbon choking at these high operating temperatures. To conclude our reactor system design, we have successfully defined the key parameters for the steam methane reforming unit as above. While in a real industrial setting, this CO rate stream will pass through a water gas shift reactor to maximize the hydrogen yield, but for the purpose of this assignment, we have assumed this conversion has been successfully executed. Therefore, the stream is now directed to the PCA unit for the final purification step to ensure our final product meets the 99.9% hydrogen purity specification.
Key species in steam methane reforming involve methane, steam, carbon monoxide, carbon dioxide, and hydrogen. To perform the calculation, we make two key assumptions. First, that all gases behave as ideal gases, and second, we use the universal gas constant, which is R equals to 8.314 kilopascal dm cubic per mole Kelvin. This allows us to use the ideal gas law, which is PV equals to nRT. For concentration, we can rearrange this to the fundamental equation, which is C equals to P over RT. The example of the calculation is shown in the slide for methane, and it is repeated for other species with same formula but different molecular mass. The strategy that we use to achieve 99.9% purification efficiency is that we use pressure swing adsorption, or PSA. It is a process that separates gas species from a gas mixture. PSA uses selective adsorption at high pressure and desorption at low pressure. It works by cycling between adsorption and desorption phases, and the operating parameters are adsorption pressure, temperature, and regeneration time. The adsorbent that we chose to use is zeolite 13X, because of its strong affinity for carbon dioxide and methane, with high selectivity for hydrogen. It also has a polar surface, large surface area, and high pore volume that makes it efficient. Zeolite 13X effectively absorbs polar molecules, which are carbon dioxide, carbon monoxide, and steam, while allowing non-polar, smaller molecules like hydrogen to pass through. It also chemically stable, non-toxic, and reusable with minimal degradation. Zeolite 13X can be easily regenerated by pressure change without solvents or high heat, making it suitable as the adsorbent. The operating conditions for the PSA process employing zeolite 13X molecular sieve for hydrogen purification are dynamic and rely on pressure cycles at a relatively constant temperature. Adsorption operated at 10 to 40 bar for selective removal of carbon dioxide and methane. Operating temperature typically between 25 to 60 degrees Celsius. PFR effluent exits at 790 Kelvin and 101.32 kilopascal, while the PSA column operates at 298 Kelvin and 10 bar. Before entering the PSA, the syngas is cooled to protect the zeolite 13X adsorbent and compressed to raise the pressure to the PSA operating level and ensuring effective hydrogen purification to 99.9% purity.
Hi, I'm Nurish, and now let's move to the equilibrium isotope of batch adsorption. Our chosen isotope is lumber isotope based on the literature where CO2 adsorption was studied on zeolite 13X and activated carbon across 25 to 60 degrees Celsius and pressures up to 1 bar. Their results show that the lumber isotope consistently achieved a higher R-squared value compared to the Freundlich, which indicate a better fit to experimental data, meaning that the lumber isotope describe the adsorption behavior more accurately. This supports our use of the Lamware isotope for modeling impurity absorption on zeolite 13X in hydrogen purification. Now, to find mass of zeolite 13X needed in the process, we need to find all values to be substituted in the batch adsorption analysis formula. So, step 1 involves calculating the volume of feed solution. PSA alternate between high pressure adsorption and low pressure regeneration. So, the cycle times control the feed volume. We selected 160 seconds per cycle based on literature which achieve up to 99.97% hydrogen purity. By using all the assumptions stated, the other hydrogen flow rate was calculated. Next, we can use hydrogen inlet mole fraction to calculate the total molar flow rate. The inlet molar volume was obtained by using the ideal gas law, giving an inlet volumetric flow rate of 5.312 meter cube per second. Multiplying by the cycle time yields a feed volume of 849.92 meter cube per cycle. In step 2, we determine the outlet concentration for each impurity based on literature values required to achieve 99.9% hydrogen purity. According to literature, the outlet mole fraction for all syngas are in ppm except hydrogen. Using the ideal gas relation, we converted this mole fraction into molar concentration and then into mass concentration using the respective molar mass. The same method was applied to all syngas and the values are included in the table. In step 3, we calculate the maximum adsorption capacity by using Lamure isotope data from previous literature. The Lamure constant and maximum adsorption capacity were taken from various studies, and these values are summarized in table 3.4.2. To find the final equilibrium update, we first determine the partial pressure for each species and then applied the Lamure isotope equation as stated in the slide. The same calculation was repeated for all the species with respective value of K and Qm. In step 4, to determine the amount of zeolite 13X needed, we compile all the calculated values from step 1 until 3 and apply the mass balance equation. Because fresh adsorbent is used, QF is assumed as 0. And from the calculation results, although the theoretical values for CO and CH4 appear extremely large, in real PSA operation these species are mostly removed by purge and depressurization steps. In practice, based on literature, H2O is the strongest absorbing impurity on zeolite 13X and it determines absorbent sizing. Based on the H2O calculation, a realistic adsorbent requirement per cycle is roughly 145 tons of zeolite 13X. For our PSA design, we use a 4-layer parallel bed arrangement with zeolite 13X. Even though it's a single adsorbent type, The multi-layer setup improves flexibility, reduce pressure drop, and also help remove impurities stepwise. From the adsorbent mass and density, each bed ends up with a volume of about 52 cubic meters. Based on literature, we assume 3 meter diameter, which is within the range of large-scale PSA system. This gives us a cross-sectional area of about 7 square meters for both column and bed. Dividing the bed volume by this area gives a packed bed height of roughly 7.4 meters. For the column design, after adding space for freeboard and distributors, each column layer is around 8.8 meters tall. Overall, for 4 layers, the overall total volume is about 249 cubic meters.
Regeneration is the process of removing adsorbed impurities from adsorbents, enabling their reuse. The regeneration method used is pressure swing, which is counter-current depressurization, regeneration, which reduces pressure and facilitates the desorption of impurities from the zeolite surface, preparing it for next cycles. This is done by lowering the pressure to slightly above atmospheric pressure, resulting in a respective decrease in equilibrium loading. The impurities on adsorbent are desorbed and adsorbent material is regenerated. Zeolite 13X systems are beneficial because pressure changes allow regeneration without any chemical solvents or high heat, keeping the zeolite 13X stable and fully reactivated, ensuring continuous production of 99.9% pure hydrogen.
To summarize our presentation, I am pleased to confirm that our integrated design successfully meet all the technical specification and production targets. Starting with the reaction system, our team selected a plug flow reactor utilizing a nickel aluminum catalyst, which proved to be the most effective configuration for steam methane reforming. By optimizing the operating condition at 910.1 degrees Celsius and 1 atm, we achieve a high methane conversion rate of 90%, and what is particularly notable is the efficiency of our design. We achieve this high throughput with a compact reactor volume of just 1.392 cubic meters and a catalyst load of approximately 1,250 kilograms. Moving on to the purification, the crude syngas is processed to our process swing absorption unit. We specifically choose zeolite 138 as our absorbent because of its superior selectivity for removing impurities like carbon monoxide and methane. Operating dynamically at 10 bar and ambient temperature, our system used a multi-layer configuration with about 145 tons of absorbent. This robust separation state is the key to ensuring we hit that critical 99.9% purity requirement. Ultimately, our integrated design delivers a techno-economical feasible solution capable of producing 30,000 metric tons of high-grade hydrogen annually, ready for industrial application. Thank you. That's all from us.